Okay, we are starting chapter 11. We're doing 11.1, which is basic concepts of probability. So chapter 10 was all the different ways we can count or make groups or selections of different things. And today we're really in chapter 11, we do a lot of the same processes, only now we're concerned about what's the probability of this actually happening. What's the probability of us getting a whole hand of cards that are all hearts? Last time we found out how many different ways we can do that. Now we're going to find out what's the probability of that actually happening. And so there's going to be a lot of similar problems between the ones we just finished up in chapter 10, but now we're going to look at them from a slightly different perspective. So this chapter starts off with some basic definitions first, and so I went ahead and listed them all here. That way, whenever we work through things, we understand what it is the problems are actually asking us of. The first two are just kind of a general thing. There's deterministic phenomenon, which are events that can be predicted exactly on the basis of observable or obtainable information. Then there's random phenomenon. Those are unpredictable events. They fluctuate or depend on a whole bunch of different variables. The weather is very random. If you flip or roll a dice, that's not random. You can really determine or predict what's going to happen there within some reasonability. There's only 6 options. It's very limited. But if I'm going to predict the weather, I mean, you guys have seen it. The weather can be off by a lot, and that's okay. So there's deterministic phenomenon, random phenomenon. Probability is just simply the likelihood that an event will occur. So what is the probability that we're going to have a snow day tomorrow? Well, given the fact that it's 75 today, the probability is pretty low. I mean, it is Missouri, and I've seen stranger things happen, but just banking that the probability is low on that. There's experiments. That's where you can actually observe or measure a random phenomenon. And so doing an experiment will help us predict probability more accurately. The outcomes are simply, what do you get? And then the sample space is the set of all possible outcomes. The event is a subset of all of the sample space. So if my sample space is all the possible numbers that a dice can be rolled on, then the event will be how many times did I get a 2 when I rolled the dice 50 times? How many times did I get a heads whenever I flipped a quarter? And so a lot of times they will have to give you that information. They're not going to sit there and have you do it. Because if I flip a dice 50 times, or flip a coin 50 times, and you flip a coin 50 times, our results are going to be different. It just is. That's what happens with an experiment. And so a lot of times in here, if they don't give you the experimental data, then we're going to do what's known as theoretical probability, or mathematical probability. That's the probability that an event occurs theoretically. If I asked you what is the theoretical probability that you're going to get a head on a coin flip, theoretically it's 50-50. You have even odds, or 1/2. You have even odds of getting a head or a tail. Those are really the only 2 options. Now, is that really what we're going to get if I sit here and flip a coin a whole bunch of times? I don't know. We'd have to do the experiment. So theoretical probability is what should it be outside of real-world circumstances? What should it be based on the information that we know? Empirical is if we actually do the experiment. And so sometimes they will give you a set of data, and they will say, we flipped a coin 50 times. Here's how many times we got heads. Here's how many times we got tails. Now tell us the probability from that data. And then we can give the empirical probability. When we are noting probability, the little symbol or the way that we note this is we note it P of E. The probability that this event occurs, whatever that event may be. The probability that we get a heads, a probability we get a tails, a probability that we roll a 6, whatever that may be. So the words and the terms that we use most are sample space, event, probability. That's about it. Event. I don't know if I said that one. So let's look at one. If we toss a single coin, find the probability that it will land heads up. It doesn't tell us that we're going to do this experiment a whole bunch of times, so we are going to find the theoretical probability. Our sample space in this case, there's only two options. We can have heads or tails. That's it. We are going to assume we cannot land on a side. That would be a pretty awesome coin toss, though. So if we only have two options, the way that we're going to find probability, the probability of getting a head is going to be 1 out of 2. There's only one head listed in our sample space, and there's a total of 2 items listed in our sample space. We're going to see that the number of the event divided by the number of the sample space equals the probability of that event that's coming up. You're going to use this a lot in Chapter 11. The probability of an event occurring is the number of times that event actually occurs over the number of items within the sample space. This next one, I need to give you a little bit more information. We're going to pretend like we are doing an experiment here in the classroom. It says, if a plastic cup is tossed, find the probability that it will land on its top. So we are going to pretend that we toss the cup 50 times. And here's our results. 44 times it landed on its side. 5 times it landed on its top, and 1 time it landed on its bottom. So if you were going to make a bet on which way the cup was going to land, you would definitely want to pick it's going to land on its side, because it lands on its side 44 out of the 50 times. But we are asked to find the probability that it is going to land on its top. Well, it landed on its top 5 times out of a total of 50 tosses, which means 1 out of 10 times it lands on its top. Or it has a 10% probability. You'll have to read the instructions on your Pearson assignments to see how they want you to leave your answers. Most of the time it will be as a fraction, but you will want to leave it as a simplified fraction unless it states otherwise. Do we have any questions at all on these first 2? All right. Flip over and look at our definition boxes. These are theoretical probability formula and the empirical probability formula. They're really the exact same thing. It's just theoretical probability formula looks at the number of favorable outcomes compared to the total number of outcomes. Empirical is going to actually consider the number of times that E occurred, or the event occurred, versus the number of times the experiment was performed. A lot of times these are going to be very similar. And we will see here in a little bit when we talk about large numbers that that's kind of the point. The more times you run through an experiment, the closer you should be getting to your theoretical probability. So this is P of E equals N of E over N of S. That's the one I wrote on the front problem, and that's the one we're going to use. And I was even nice enough that I did not make you come up with these trees in the next one. It says Kathy wants to have exactly 2 daughters. Assuming that boys and girl babies are equally likely, find her probability of success for the following cases. If she has a total of 2 children, or if she has a total of 3 children. What are the odds or the probability that she can have 2 girls? Now this problem was designed so you would have to do the tree diagrams in order to come up with her possible outcomes for the genders of her babies. I went ahead and included them just to shorten it a little bit, but if you had to come up with it, remember that for the first child there's 2 choices, second child there's 2 choices, and then we're only concerned with the outcome that produces a girl-girl. That's the one we're interested in. So if I'm looking at the total number of outcomes, there was four total varieties, I guess you could say, of the different outcomes for her children. She could have had girl, 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 boy, boy, girl, or boy, boy. So if I want the probability of girl, girl, that would be the number of times that girl, girl happens versus the number of times in my sample space. Well, girl, girl only happens one time out of 4. So she has a 1 in 4 chance of having 2 girls, or a 25% chance, theoretically. Now, if we do the same experiment, or we look at the same tree diagram, we just don't stop at the 3rd child. We go on and we do it again, because now she has 3 children. So how do we get at least 2 girls, or exactly 2 girls, out of 3 children? So we're not concerned with girl, 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 because it says that she wants exactly 2 daughters. That word exactly is going to be really important in your problems. Sorry, I circled it and you can't see that. Exactly 2. That means you can't have 3. You can't have 1. You want exactly 2. And that happens here, and here, and here. So it happens a total of 3 times. So the probability that she's going to have 2 girls happens 3 times out of 1, 2, 3, 4, 5, 6, 7, 8. Again, if you had to come up with a tree diagram, every time she has a child, she has the option of having a girl or a boy, and you just keep listing the possible outcomes. The big thing to key in on it is the fact that she says exactly 2. And so we only look at the ones where there's 2 girls listed. None of the rest fit her requirements. Are there questions on that one before we do one that's a little bit more interesting? Okay. This next one's on, I think it's on the practice final. I don't remember if I put one on there or not, now that I said that. All right. Probability, we're going to deal a lot with cards. Those are pretty straightforward. It says, find the probability of being dealt each of the following hands in a 5-card poker with no wilds. Use a calculator to obtain the answers to 8 decimal places. So that's a lot of decimal places. 8 decimal places. Don't want to forget that. We want to know the probability of getting a full house. And so here's the nice thing. They already did a table for you. They made this wonderful table where it tells you the number of favorable outcomes for getting a royal flush, or getting a straight flush, or getting 2 pairs. They already did all of these calculations. But just as a note, we can actually find all of these calculations by doing combinations, which is what we did in Chapter 10. So if you weren't given the table, we would be able to find it. But for things like full house and royal flush, it's a little bit easier to look at the tables than having to figure out the different combinations necessary. But this is what we did at the end of Chapter 10, when it was how many different ways can we get a hand that's all red, or get a hand that's all spades, or draw a king, and things like that. We were doing all of this in Chapter 10, and it doesn't go away now. So we want to know, what is the probability for a full house? That's our first question. So if I'm trying to find the probability of a full house, then I need to look at the number of times we get a full house over the number of hands total that we can get in poker. Well, the number of times you can get a full house is 3744. There's 3,744 different ways that you can get a full house. And total, it's all the way down here at the bottom, there's 2,005,980 or 960 different possible poker hands. We found this number by doing 52 combination 5, choose 5. 52 standard cards, we choose them at a rate of 5 at a time. That gives us the 2598960. We did this back in chapter 10. And we can do that similarly for all of these to figure out different ways that we come up with the number of royal flushes or straights or whatever. But by getting the table, you don't have to do the combinations. So if you type 3744 divided by 2 million into your calculator, and we're going to round to 8 decimal places, we get 0.001444058. So if you remember how we go back and forth between decimals and percentages, we have 0.144058% chance of getting a full house. So when you go and gamble, that's your chance of actually getting a full house when you play poker. Not very good. Not very good at all. So you may want to second guess when you go betting. Our second one is asking for a royal flush. Royal flush is like the ultimate hand in poker. It's the one you want. That's where you have the 5 highest cards of any denomination or any suit. You have the ace through the 10. So the probability of a royal flush is going to be the number of times you can get a royal flush over the total number of hands again. Well, according to our table, there's only 4 different ways we can get a royal flush. And that's because we can get it in each of the suits. We can get it in diamonds, hearts, clubs, or spades. So there's only 4 ways we can get it, but there's still 2.5 million different hands that we can get in poker. So if you type that into your calculator, you get 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 1, 5, 4. So if I move this into a percentage, it's 0.000154%. Not very good odds in my favor that I will ever get a royal flush. So just remember that next time you're at the casino or next time you have a poker night at your house. If you actually get one of these, it's very rare. Do we have any questions about how we found that? All right, bless you. Let's do another one with population. It says, according to the United States Census figures, on July 14th, 2028, I feel like I might have typed that wrong because it's already telling me what it was. It was probably 2020 or 2018, one of the two. We're going to go with 2020. There were an estimated 162.4 million males and 166.9 million females. If a person were selected randomly from the population in that year, what is the probability that that person would be a male? So we need to figure out the probability we pick one male. Well, probability is going to be the number of times that event occurs, so the number of males, over the total. I'm not going to put number, I'm going to put total population. Again, every single one of these problems, even though they're worded differently, I'm still using that same formula right here. The number of the events over the number of the sample space. If I want the probability that I'm going to get a man, then I need to know how many men do we have over the number of people in my sample space. And that's what I'm doing here. So it told me that I had 162.4 million males. And I had a total population. It doesn't tell me my total population. How do I find my total population? Or can I? Yeah. We're going to assume, for the sake of this problem, that there's only male and females in this census. And so if I need the total number of people, then I would take the number of males and I add to that the number of females. And that'll tell me the total number of people represented in this population. So you type 162.4 divided by 162.4 plus 166.9. Make sure this is in parentheses when you type that into your calculator. Then you're going to get 0.493. And again, your problems will be very specific on how many decimal places to round to. But if you notice, if I were to make this into a percentage, basically it's 49% chance that I'm going to select a male out of the general population, which makes sense because if you look at the numbers, we do have more females represented in this data. So I should have slightly higher odds of selecting a female randomly than selecting a male. If it was equal, if it was 162 million and 162 million for female and male, then theoretically I should have a 50-50 chance. Any questions? Clarifications? All right, let's talk about large numbers. The law of large numbers, aka the law of averages. As an experiment is repeated more and more times, the proportion of outcomes favorable to any particular event will tend to come closer and closer to the theoretical probability of an event. So what that means is if I only run an experiment twice, it may not be anywhere close to what the theoretical probability is. If I flip a coin and I get tails, and I flip a coin and I get tails, I just showed that there's a 0% chance of heads. And that's not true. Theoretically, there's a 50% chance of getting a head on a coin flip, but because I only did the experiment twice, then it doesn't look that way. I have to repeat that experiment over and over and over again, and the more times I repeat it, the closer I get to that average. And so this next problem would require you to do a lot of data crunching, and I'm going to do it... let's see. I did it 10 times in my notes, so I guess I'll do it 10 times here to show you how it fluctuates a little bit based on how many times you actually run your information. Here we have a fair coin is tossed 35 times, producing the following sequence of outcomes. And they separated it into groups of 5 just to help us keep track of what's going on. So the first flip, they got tail, tail, and then head, head, heads, tail, 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 so on and so forth all the way through. There's 35 coin flips here represented. It says calculate the ratio of heads to the total number after the first toss, the second toss, and so on and so forth through all 35 tosses, and then plot these ratios on a graph. Now, I'm not making you plot them on a graph. Pearson will not make you plot them on a graph. Pearson might have you pick out a graph that matches or look at a graph and see what it says, but they're not going to have you actually graph it, so I'm not either. I'm going to have you look at a graph and see what's going on. But here's what's going to happen. We're going to look at toss 1, and we are comparing heads to the total number of tosses. So if I look at toss 1 was a tail. So I had 0 heads compared to the total number of tosses. So I had a 0% chance of getting a head on that one. If I look at toss 2, again, it was not a head. So I have 0 heads still compared to my 2 tosses, which is 0. For toss 3, I finally have a head. I finally got a head on that one. So I have 1 out of 3, 0.33. Theoretically, my theoretical probability, I think I spelled that wrong, is 1/2, or 0.50. That's what I should be getting. Well, I didn't get that here, here, or here. So that's why the more times you repeat an experiment, the closer you're going to get to your theoretical probability. So after 4 tosses, that was another head that I got. That'd be 2 out of 4. That matches our theoretical probability exactly. Then we go to 5. I had 3 out of 5 then, because that was another head. That gives me 0.6. For 6, I got another tail, so I have 3 out of 6. For my 7th toss, I got another tail, so I have 3 out of 7. Can you still see these? Yes. For my 8th, I still got another tail, so it's 3 out of 8, 0.38. By toss 9, I finally got another head, so that's 4 out of 9, 0.44. At 10, I got another head, which is 5 out of 10, which is 0.50 again. Theoretically, you're supposed to do this all the way through those 35 tail or head tosses. I'm not going to make you do that. We're going to go ... And we're going to look at what happened on the last toss. And we're going to see how many times we got it. So if I go through and I count the number of heads, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. I have 18 heads listed. So I got 18 out of 35 tosses, which is approximately 0.51. That's pretty close to our theoretical probability. But notice how it fluctuates during our actual experiment. If I would have only tossed the coin 3 times, I would have said the probability of getting a head was only 1/3 of the time. That's pretty far off from here, which is why scientists will repeat experiments over and over and over again, because they want to make sure it's accurate, that it's not a fluke, that it actually does hold up this way every single time. And if you look at the chart that I presented, which is the one they tell you to make, our theoretical probability should be 50%, which is why there's a bar there representing that. All of this jagged craziness is our actual probabilities that we are finding. Notice it stayed down here at 0 for toss 1, toss 2. But by toss 5, we were at 60%. So it was up here. And so we plotted all of these points. And notice the more times we do it, yes, we're still fluctuating some, but we are hovering right around that 50% mark. That is the law of averages, or the law of large numbers. The more times you repeat an experiment, you should be averaging out or getting closer and closer to our theoretical probability. Questions, comments, clarifications? I will not make you do probability on 35 head tosses and tail tosses, because that gets exhausting. But we did do 10, so we could see how it does fluctuate a little bit. All right, at the bottom of this page, it says comparing our empirical and theoretical probabilities. I thought this was a good little box. It says a series of repeated experiments provides an empirical probability for an event, which by inductive reasoning is an estimate of the event's theoretical probability. Increasing the number of repetitions increases the reliability of that estimate. The more times we toss our coin, the more accurate our empirical probability becomes. Likewise, an established theoretical probability for an event enables us, by deductive reasoning, to predict the proportion of times the event will occur in a series of repeated experiments. The prediction should be more accurate for the larger numbers of repetitions. So by doing the theoretical, we can kind of have like a goal of what should be happening empirically. And if it's not happening, we can increase the number of times we're conducting our experiment to see if that's going to get us closer, because it should, as long as we've done our math correctly. All right, let's flip over. Let's switch a little bit. We're still in math, but we're going to talk a little bit about genetics, and hopefully this will bring back some grade school, middle school science. Probability within genetics. Hopefully everybody at some point in their life has heard the name Gregor Johann Mendel. Probably known him for like a pea plant. That's usually what's brought up in grade school or middle school. He's the one that came up with dominant and recessive genes. And a lot of times this is presented with eye color, skin color, hair color, the color a flower will turn out, or that's another common way that this shows up. That's pretty much it. But what happens is dominant genes are going to be represented with a capital letter. Recessive genes are going to be indicated with a lowercase letter. And when a dominant gene is connected to a recessive gene, the dominant gene is the one that holds out, the one that gets shown or represented. And so when we are looking at eye color and we're looking at what's going to happen, we can look at who has the dominant genes and who doesn't. Or if we're looking at plants, then we can say, okay, what's the color combination that we might be able to get from this? If you look at this, I think these are kind of interesting. First and second generation. So if we have like a mom and a dad here, and the dad has brown eyes and the mom has blue eyes, notice that theoretically we should never have blue eyes if that's what this is actually representing. This is not what it's representing. But notice all of the pairings, if the other parent has recessive, they're all going to be dominated out by the dominant genes. And so that offspring is not going to have an opportunity to have the recessive gene pop up. But if we have a recessive and a dominant gene for each parent, there is an opportunity for that recessive gene to actually show up over here. So I find that really interesting. And so we're going to predict the probability of plant colors. We're going to use our table 3 to determine the probability that a third generation offspring will exhibit each flower color. Base the probabilities on the sample space that are equally each of these are equally likely to happen. There's 1 in 4 chance of this, and this. So red is our dominant color. White is our recessive color. Recessive. So red is going to be indicated with a capital R, white with a lowercase r. So if I'm looking at table 3, how many different times will I get a red flower? If the red will always show up if there is a capital R. Yeah, definitely going to be red up here. Here we have recessive and dominant and recessive. So the dominant trait will overpower or dominate the recessive gene and be shown. So all 3 of these are going to be red. So the probability of getting a red flower is the number of outcomes that we get red over the number of the sample space. Well, we got 3 out of 4. 3 out of 4 chances that we're going to get a red flower. So it's much rarer or much harder to get a white flower, because white flowers were only going to show up if we have RR. RR only shows up 1 time out of the 4. Now, genetics aren't quite this easy because it's not always equally likely that certain outcomes will happen. But in a theoretical space where all the outcomes are equally likely, you can make some predictions about what's going to happen. So dominant and recessive genes, the big things here are if there is a dominant gene connected, the dominant gene will always win out. All right, let's talk about odds. Again, we're not really learning anything new. We're just talking about the same thing in a slightly different format. If all outcomes of a sample space are equally likely, and if A of them are favorable to the event E, the remaining B outcomes are unfavorable to that event, then the odds in favor of E are A to B. The odds against E are B to A. Basically what we're doing is we're writing a proportion to tell us what are the odds in favor of the certain event happening or the odds against this certain event happening. This is like you go and play poker, or you go to a racetrack, or you're making a bet on a basketball game or whatever it may be, and the odds are 2-1 in favor of blah, blah, blah winning. Or the odds are blah, blah, you can do that. That's where these odds come into play. It's right here. It's a proportion. And one thing to note about proportions is they need to be simplified. So we want to make sure that all of our proportions are simplified. So let's look at Teresa. Teresa has been promised one of 6 jobs, 3 of which would be intern positions at the state capitol. All right, so I'm going to make I like to keep notes when I do word problems if I can. She has 6 job options. 3 are interns or internships, and 3 of those are not internships. That's what we know. If she has an equal chance for all 6 of these jobs, find the odds in favor of her getting one of the intern positions. So this one's a little bit of a blah problem. Because what are the chances of her getting an internship versus not? Yeah. Half of the jobs are internships, half of the jobs are not. So if she randomly selects one, she really has it's half versus a half or 1-to-1 odds. This one's not very interesting. She has a 50-50 chance or a 1-to-1 odds because there's 3 for internship and 3 not. So we'll do another odds one. That'll actually be more interesting. But I do like this one simply because it does show you the odds can be equal. You can have an equal probability or chance of being for and against something. So Teresa's not very interesting, but Bob's got a little bit more going on here. He bought some tickets. He purchased 12 tickets for an office raffle, in which the winner will receive an iPad. If 104 tickets were sold altogether and each has an equal chance of winning, what are the odds against Bob winning the iPad? Against him. So right now we know there was a total of 104 tickets sold. We know that Bob bought 12 of them. So if we take 104 minus 12, we find out that there was 92 other tickets sold. These are the ones that are against Bob. There's 92 chances for somebody else to win. There's 12 chances for Bob to win. So when we're finding the odds against, we're going to put against to Bob. Well, there's 92 against him to the 12 that he purchased. So we need to simplify these. I know they're both even, so if I divide both by 2, I get 46 to 6. Those are both even, so I get 23 to 3. The odds against Bob are 23 to 3. Odds aren't very good for Bob. But they're also not horrible if you think about it. I mean, if we found the probability that Bob would win, we'd be looking at 12 over 104. That's 10%. He has a 10% chance. That's not too shabby for an iPad. So your problems can ask you for odds. Your problems can ask you for probability. Your problems can ask you, like back in chapter 10, for combinations. You know, how many different ways can they select Bob's ticket? So none of this stuff goes away just because we've moved on to a new section. But you do need to pay attention to what the odds problems, whether you're for or against. Because if we were for Bob, then this would be flip-flopped, and it'd be 3 to 23. So the order matters based on what we're doing. Does that make sense? Okay. All right. So probability and odds go hand in hand. So this is how we go back and forth between the two. If E is our event, then the probability that E happens is going to be A over B. Then the odds in favor of E, of that event, are A to B minus A. Because remember, B is the total number in our sample space, and that's actually what we did up here. We took the total number and we subtracted the number of tickets Bob got to get to the ones that are against him. That's what this is saying right here. So the probability of an event is going to be the number of times we have that happen over B, and then we can compare that as A to B minus A. If the odds in favor of E are A to B, then the probability of E is going to be A over A plus B. It's just going frontwards and backwards of the same thing. So we're going to use this to figure out what are the odds that it's going to rain, against raining, I guess. It says there's a 30% chance of rain tomorrow. What are the odds in favor of rain, and what are the odds against rain happening? A 30% chance of rain. So that means the probability that rain happens is 0.30. Now, that does not look like a fraction. So we're going to make it a fraction. How do you think we'll make that a fraction? That's exactly right. We're going to stick that bad boy as 30 over 100. If I multiplied this by 100, I move everything to the right, and we can go just straight to that. You don't want to put a decimal as like 0.30 over 1 and say that that's our fraction, because that doesn't really, we don't like fractions combining with decimals if we can avoid it. I am going to choose to simplify this since they both end in 0 to where I have 3 over 10. 3 is my top number, that's my A. 10 is my bottom number, that's my B. So the odds in favor of rain are going to be 3 to 10 minus 3, or 3 to 7. Odds in favor of rain are 3 to 7. We don't typically speak of the chances of rain like that. We usually speak of 30% chance of rain. But we can talk about odds as well. And then the odds against rain are going to be flipped. They would be 7 to 3. The odds for rain are 3 to 7. The odds against rain are 7 to 3. So there's actually a higher probability or a higher likelihood that we're not going to get rain, is what the odds are really showing us. Questions? All right. One more. It says in a certain sweepstakes, your odds of winning are 1 to 99,999. What is the probability that you will win? So here we're going from odds to probability. So that's our second step here. Odds to probability is where we're going to take our A and put it over A plus B. Our A is 1 and our B is 99,999. So the probability that we have any chance of winning will be 1 over 1 plus 99,999, which is 1 over 100,000, which is 0 with 4 zeros. 1, 2, 3, 4, and a 1. We have 0.001% chance of winning this sweepstakes. It's not very good. But, as Dumb and Dumber would say, there's still a chance. If you haven't seen that movie, because I know y'all were born after the 90s, you should go watch it.